Now, what is missing is in this chapter of the PI controller is the calculation of Kc. Of course, we again use the second Nyquist equation. Total open loop gain at omega d must be 1, and we should now write down the parts of our magnitude. We have the controller magnitude and we have the process actuate both values at omega d. This must be 1. This comes from curve. Let's do this first. In our curve we can find that the value for the magnitude at 1.4 is a little bit less than 6 dB. If you look deeper in this magnitude curve, then we see this will be 0.6 dB. Yeah? This is calculated, or the result of this comes from the cursor function of the numerical simulation. But if we have this on paper, of course, we cannot read this value better than plus or minus 1 dB. So I think, say 0.6 dB magnitude. This is a value near 1. 0.6 is a little bit larger than 1. 0.6 dB. So from curve, 0.6 dB equivalent to 1.07. And what is this? That is a controller magnitude at omega d, and we have to have a quick look on this function. Note that the controller transfer function is written here, and now we have to write down the magnitude of this if p is replaced by j omega. So we have to calculate the following expression. The magnitude value is Kc multiplied with 1 plus pt term gives Pythagoras 1 plus omega Tn squared, and we have to calculate this value at omega d divided by j omega Tn, and the denominator gives the magnitude omega d Tn. Omega d is given, Tn is 1 second is given, so we can calculate this value to Kc times, I write it down. This is 1 plus omega d is 1.4, this is 1 second, so this is 1.4 squared divided by 1.4. And both together, we put this into the Nyquist equation. This comes from the curve, and then we can solve. Kc is 1 divided by square root 1 plus 1.4 squared multiplied with 1.4 divided by this value 1.07, and if you put these numbers in your calculator you get I calculate 0.76. So the Kc is now given, the Tn is given, design is ready, design completed. Kc is 0.76, Tn is 1 second. You can build it and we can simulate it in our simulator. So I go to this curve. I think we can do the comparison with my integrator, and before we do this we have to replace our I block. I mark it, you see the points here, click the delete button, and add now the PI block here. In this case, the PI parameters are 0.76, 0.76, and the time constant is 1 second. Say OK, calculate the curve. I store this, and the PI controller, you see, final value is very fine at 1, much faster than this. Forget the red curve, just work with the green curve, that's okay. So at this time, to have a good curve diagram, I delete the last both curves. I go down to 10 seconds, say 5 seconds, and recalculate the PI controller, and you see here, this is the relevant curve. I think I should cut also the P controller at 5 seconds. I can do this with the right mouse button with the pull up menu. Blue curve at this point, cut the curve, yes, and then make auto scaling. So in this case, you see, this is a PI controller with a maximum point here at 1 second, slower than P. The omega d value is smaller, so we are not so fast, but the final value is exactly correct. Yeah, this is the decision. If you go with the PI controller, forget the pure I controller. In this case, it plays no role here in this situation. Okay. Yeah, finally, let's compare the speed indicator. Speed indicator. The Tm value, Tmax of the reference step response should be 4 divided by 1.4 second. This is round about 2.9 seconds. Is a prediction of my speed indicator, and the simulation lays by 2 seconds. So the prediction here is a little bit larger. So you can see in general the prediction value is a little bit, is 30-40% too large. So in reality we get faster systems than predicted, but doesn't matter. The comparison factor is good enough for us. Yeah. Okay. Yes, in the student paper, you can see we have added a realization I should do on my paper. How can we realize this controller with operation amplifier circuit? This is very simple with the following calculation values. Note that we have discussed this circuit of a PI controller in chapter 3. We need an operation amplifier with ideal differential gain. Have here R1, R2, and a capacitor. And note that this controller has a negative gain. That's an inverted amplifier. Note furthermore that it is possible to add a second input with resistance R1. Then you have an adder. Yeah, the currents through R1 and R3, if this is also the same size like R1, are added here in this point. So here both voltages are added, and this gives the possibility with very simple steps to calculate the control difference. If one of this signal is inverted, that makes the adder to a subtractor. Okay, how large are R1, R2 and capacitance? We can say the equations very simple. R2 times C is our Tn, should be 1 second, and R2 divided by R1 is our Kc. Kc is 0.0 0.76. The product here is 1 second, is rather large. Capacitances which are should not be electrolyte capacitor. The largest possible non-electrolyte capacitor which can be paid is 10 microseconds, 10 microfarad, but this is also a big thing, costing round about 10 euro. So it could be a good idea to make C as a selection small, say C is 1 microfarad. Then we can calculate the R2. R2 then is 1 mega ohm. If the input current is small here for the negative input, and this it will be small if we take feed effect input operation amplifiers like Texas TL076 or TL0664 and so on. These are feed effect input stages. So 1 mega ohm is not a real big problem, no? And R1 can be calculated then. R1 is R2 divided by Kc. In our case, 1 mega ohm divided by 0.76. This will be, let's type in 1.32 mega ohm, and then you can build it. Yeah, that is the one possibility. What I have also seen in the student paper, that I skipped through the different types of controllers on page 16 and check if these blocks can be used as a controller. Let's do this job. Check other types of controllers of page 16 in workbook. Note negative phase makes loop slow, positive phase makes the loop fast. Yeah? So let's skip through the list of page 16. I switch to page 16. Let's look for a PT1. Can a PT1 block be a good controller? This is a PT1 block, transfer function, this is a phase. You see the DC gain is still K, so it could not be more accurate than a P block. And what is with the phase? The phase is more negative than P, so we can say a PT1 is worse than P, slower, caused by negative phase. Yeah, slower. So there is no sense to use a PT1 block as a controller, because we add negative phase compared with a P controller, and that gives no advantage but only disadvantage, decrease of speed. Next block in the list is a PT2, same for PT2. So we can say PT1, PT2. It is senseless to use these as a controller. Okay, I is discussed. What is it about an IT1? IT1 has best accuracy compared with I, same accuracy, but you see the phase of the I is constant minus 90. In the IT1 has an additional PT1, so the phase is more negative. So we can say IT1 best control error, but slower than I. I is slow, and IT1 is much slower, so forget it. No controller with type IT1 will be ever seen in the world. Okay, now we go to the section of the D blocks, 6, 7, 8. The D block has positive 90 degree, could be lead to very high omega D values, high speed. The DT1 also has positive values going to 0, and the DT2 positive 90 now going down to negative 90, depending on the position of omega D, faster or slower, yeah, DT2. But there is a big disadvantage of block 6, 7, and 8, D, DT1, DT2. You should keep in mind, yeah, D, DT1, DT2 could be faster, but what is with the control error? X, D, T goes to infinity. Note our equation is still valid. 1 plus controller at 0 times process actuator sensor at DC value. The DC value of our process, including actuator and sensor, cannot be changed. That is given. In our 4PT1 case, it is a value 2. The controller DC gain can be influenced by the type. And now let's look on the DC gain of both 3 blocks, starting with a D here. P0 means DC gain 0. P0 means DC gain 0. P0 means DC gain of all these 3 blocks is 0. Z, yeah, DC gain of these blocks is 0. That means this is 0, independent of this size. This is 0, so the control difference is 1, means 100%. That means x of t goes to infinity is always 0. And that means you want to have a cruise control system, want to drive 100 km per hour, and what happens? The car stops. Yeah? So you cannot use these 3 types of D blocks in spite of the positive phase that may be nice. The DC gain is 0. That leads to the fact that you have always controller output 0. The system cannot work properly. Yeah? Forget it, cannot be used. Okay, you see in the list of the blocks, the next is the PI we have discussed already. The next video will show a different choice of TN, not pole compensation. There are other choices of TN, and I will show you advantages and disadvantages of this new choice. That is the chapter 5.2.6 in the new video. This is now stored in video number 43. 53, sorry. 53. Thank you.